Okay, so thank you everybody for being here today. Philippe Ciblat, professor at Telecom Paris, will talk about green digitalization. Thank you, Philippe, for being here, and whenever you want.
Okay, thank you. Thank you for the invitation. So we'll talk will be not very technical. Okay, it's more a discussion or some reflections about the environmental impact of numerical techniques, and more specifically of wireless networks. Okay. So I have three parts. Okay, one with some figures of some data to see what is the impact of the wireless network on more generally of the numerical technique on the environment. The second one, which will be quite short, is about the materials. And the last one is more specific about wireless networks with some technical point. So just some figures. So for starting, so some data. So here we have not exactly the number of smartphones around the world, but the number of sales of smartphones per year. So you can see a very big increase during this the first phase. So typically during the 4G, okay, and the introduction of the touch screen. Okay. And then now we have a floor, okay. So not in number, but just for the number of cells. And so we have a floor now, okay. So it's not there is not a big increase now, okay. And here we have the traffic. So if you look at the traffic, we have a big increase, okay, and the increase may depend on the applications, okay. So here we have the number of WhatsApp message. So WhatsApp active users per year, and you can see that we have a linear behavior. Okay, so we have an increase, but it's not an exponential increase. It's linear, but it's already quite large. Okay, because you can see that the percentage from one year to another one is typically around 20% here. Okay, and obviously in 2020 it's a little less. Obviously, it is not less, it was exponential. Okay. So it's not necessarily exponential. Okay. Usually, when you read a lot of paper, you can see there is an exponential growth of the traffic or an exponential growth of the number of phones. It's not necessarily the case. Okay, you have a growth. The growth can be high in the sense that the percentage can be high, but the percentage is not necessarily constant. Okay, you have an evolution of the percentage per year, and finally, if you look at the behavior, you just see a linear behavior, but the slope is quite sharp. Okay? But it's linear. So be careful, okay? So here it's for WhatsApp, and here it's for SMS message. And what you can see here with both curves is, okay, you have two applications, and one application which corresponds to WhatsApp may include the second one, because you can send message on WhatsApp like SMS. But you can see there is no replacement. Okay, you have also an increase, but more logarithmic increase of SMS traffic. Okay, during the same, almost the same period. Okay. So you have more an accumulation of all the tools than some replacements from some tools to other tools. Okay. And on the right, it's the traffic. So here, whatever the application. Okay. It's the traffic for wireless mobile network, if I well remember, in France. And once again, okay, you can see that, so here it's 17, 18, 19, and so on. So here we are in 24, okay? So the data are very recent, okay? For the left part, for the right part, okay? And once again, at the beginning, you can see, at the beginning, so it means a few years ago, okay, you can see an exponential growth, and now it's more a linear one, okay, once again. Okay. And in black, it corresponds to the growth per year. And you can see that the growth rate decreases each year. Okay, but it's still high. Okay, here it's 20%. If I really remember, it's 20%. And now it's more linear, like WhatsApp. Okay, so in France, and especially in Western countries, you can observe more a linear increase of the traffic. And if you look at now the data centers, so not the traffic, but the data centers, obviously, once again, you have an increase of the data center. So here we have two figures, actually three, but so this one corresponds to the energy consumed by the US data center. So in a solid line, it corresponds to the reality. So it corresponds to the past, and it corresponds to some measures. Okay, but you can see that some papers are not disagree with the measurement. Okay, but you have the trend. Okay, and in dashed line, you have the expectation. Okay, for the future. Okay, and here, in contrast to the previous slide, we expect an exponential behavior. Okay. So it means that the growth rate is constant. Okay. So here it's for the US, and here it's not only it's in terms of energy. Okay, in terms of energy. So that's for the US, and here it's worldwide. Okay. So the trend is exactly the same, just the y-axis is larger, but the trend is exactly the same. And here you have exactly. So once again, it's for the US here, because this point corresponds to this one. Okay, but now you have a decomposition of what's happening in a data center. Okay, and what you can see here. So here it's for the infrastructure. Here it's for the storage. Here it's server, and here it's for AI. Okay. And what you can see that the increase, the expected increase, so for the future is related. We imagine, okay, not necessarily true, okay, but we imagine that it will be related to AI application, okay. AI computation or AI application. And therefore, data center now, it's more for computation. It's more computation center than storage center now, in terms of energy. For a near future. Yeah. Yes.
When you say infrastructure, do you mean to produce the infrastructure or to keep it on?
No, just to I think it's just to manage a network.
Okay.
Just to manage a network, and so all the infrastructure I think coming from some providers. But for me, it's close to network. Network, I think, is just a network inside the data center. And so this part, yes, and you can see that storage is a small part finally. And so here for data center, we imagine an increase growth. While for the traffic, more linear growth. Even if the slope is sharp, okay? So. And now, if we want to have a global view, okay, in terms of energy consumption, so for ICT, so ICT is information and communication technology. Actually, what we consider in ICT is not necessarily so clear. Okay, so for example, embedded system in a car is not in ICT. ICT is more. But television is in ICT, for example. So it means that if you consider all the information and communication technology, especially embedded system, it's more. It's more than that. Okay. So ICT corresponds roughly, but it's very roughly, to 4%, okay, 3 or 4% of the total greenhouse gas emission. So here now is not in energy, okay, but it's in emission greenhouse gas. Okay, so obviously it may depend on how the energy is used, on which energy is used. Okay, and on the energy consumption, so we have several trends. So we have already seen some of them. Okay, in terms of traffic, it's more linear. In terms of computation, it's more exponential. Okay. But we have some part for which it's less. Okay, we have a decrease. Okay, so especially for the TV. Okay, because we have less TV. Okay, even if TV now is bigger, we have less TV. And for so the personal computer, okay, so not laptop, but just desktop personal computer, usually there is less desktop. So we can see some, you can find some, so some particular points or some particular devices where you can see a decrease, but globally you have an increase. Okay, and here we have some figures. So this one corresponds to so the emission in GHG. Okay, and here we have some expectation for the future. And as you can see, there is a big gap between some expectations. Okay, so it really depends on the paper. It really depends how they calculate, what they consider, which scenario they will consider. Okay, so it means that the expectation, especially not in the near future, but in quite so for example in 2040, obviously is not precise at all. Okay, and sometimes just, I put the figure on the right because you should be very careful. For example, on the right, you have the electricity consumption. So now it's not GHG emission, but it's really energy consumption for mobile providers in Europe. So it's very easy to calculate. Okay, you just have to consider the electricity bills of each provider. Okay, and some researchers have done that. Okay, but for example, when you have an electricity bill for Orange, you have the wireless network of Orange, but you have also the shops of Orange. You have also the cars of Orange, and so on. Okay, and so be careful because, for example, if now you look at in details, okay, here you have the old telephone, so the PSTN, okay, network, and obviously you have a decrease. Okay, here you have the office, the stores, the cars, okay, and here you have a decrease. Okay, but if you want to look at just the wireless network, and typically if you want to see the impact of 5G, okay, if you want to see the impact of 5G, so here it's not 5G because it's just until 2080, so it's just until 4G, okay, you have an increase. Okay. So globally, if you look at European network provider, the consumption between 15 and 18 is constant. So you can say very good. Okay, it's constant. But what is constant? Nothing actually. So the wireless network increases, but the shops decrease. The shops, the offices, so typically due to teleworking, and just the shop because they just want to close some shops and to reduce also the cars from Orange and so on. Okay. So be careful with some figures. You really have to look at the details. It's very easy to see absurd things. Very, very easy. Okay. Okay, so that's for the figures. So just a very simple vision. And in terms of material, so obviously, as you know, the first idea is not necessarily the first idea, but it was very common to say, okay, if you use ICT, you do dematerialization. Okay, you need nothing. Okay, it's virtual, it's a cloud, and so on. So obviously, ICT is not virtual at all. Okay, and because you have a lot of devices, and so you have a lot of materials. Okay, so here just some examples. So here it's a data center. So it's a project of a data center in Paris. Okay, so it's not exactly in Paris, but it's in La Courneuve. Okay, so near the motorway A1 from Paris to Roissy. Okay. Here it's what you can see inside a data center. So I suggest you to visit a data center. It's very impressive. And, I don't know if it is easy. I succeeded to do it. Okay, thanks to the school, not by myself. Okay. So there is a one data center which is quite close to here in Marcoussis or in Villarceau or in Nozay. I don't know exactly what is the name of the.
There is one in Marcoussis.
Yeah, one in Marcoussis where Alcatel was.
And they are building
Yeah.
another one. Sorry, there is one in Marcoussis for many years now, and it was Data 4, yeah.
Data 4.
And they are building other ones in Nozay where Nokia was before. I am from Nokia.
Yes. Yes, formerly it was Nokia, and even formerly it was Alcatel.
Yeah.
And it's very impressive to visit, especially this one.
I didn't.
Okay, if you can do it. And here just a mining, so it's I think it's a lithium mining in Canada. I think it's in Canada, if I well remember. Okay, but just more details. So if now we want to see some. So for example, if you consider data center, so first the consumption. So worldwide now data center is about 460 terawatt hour. Okay, so is it high or small? It depends. Okay, but this number, it's more than all the French nuclear plants. And it corresponds to 2% of worldwide electricity production. So therefore, it's very difficult to say, is it high, is it small? So when you see it's more than all the nuclear plants from France, it seems to be high. When you say it's just 2% of the worldwide electricity production, you can say it's nothing. So once again, it's very difficult to have a message about that. Okay. And what is the issue? So the first issue, obviously, just you need energy to do computation, okay, or to do storage. Okay. But obviously, the second issue, and where you can have perhaps a big impact, is the cooling. How to cool these data centers. And obviously, there is already one solution, okay, which is quite energy friendly. Okay. Is to use a free cooling by water, so just to use water to do cooling. So you use less energy, but you have two other problems. So you transfer your problem from one to another one, and actually to two over one, to both. You may have a biodiversity issue just because you use water, so you transform the water cycle. Okay. And typically you increase the heat of the water. Okay, that's the issue. And you may have also a use conflict, okay, because water is quite scarce. Okay, it's the scarcity. And so you obviously you need for irrigation or sometimes you have to select for irrigation or data center. Okay. And so, for example, if you want some figures about that, so we can introduce two parameters to see the efficiency of a data center. So one related to water and one related to power. Okay. So perhaps I will use the first. So the water usage effectiveness. So it's just the number of liters you need to operate an amount of kilowatt hour. Okay. And now it's about half a liter. Okay. And so that's the value. And obviously, for future scenarios, you have an increase. So it's less efficient in terms of water because you want to do cooling with water in order to reduce your energy consumption. So if you want to be efficient in energy, you will be less efficient in water. And it's exactly what you can see on the PUE, which is the power usage effectiveness. Okay, so that's the ratio between the energy consumed by the data center over the energy needed for doing the computation or the storage in the data center. And now the best one are close to 1.1. Okay, so you are very close to the optimal, because the optimal is 1. And it's exactly what you can see here. Okay, so that's the PUE. So the best one is around 1.1, but in average now it's 1.4. And so we expect to have an improvement. Okay, but this improvement will imply a degradation on the water usage effectiveness. There is a trade-off to. There is a trade-off. Okay. So you can also use, it's not in the slide, but you can also use, if you want, or if you can, not necessarily if you want, the heat produced by the data center. Okay. But for that, for example, the data center has to be close to some housings. So typically it has been used during the Olympic Games. So I think one data center near Sydney was used and is still used to produce hot water from the Olympic swimming pool and some Olympic villages, so some flats from the Olympic village. But for example, in Data Force or in Marcoussis, they cannot do that because there is nothing around. There are just some fields around the data center. So finally, they cannot use the heat for housings. There is some housing, but it's small villages. They tried to do, but they didn't succeed actually.
What I know is that for Nausée, there are some plans to reuse the heat
But in Data
for
Force,
Nausée.
they didn't.
But in Marcoussis, I don't know. But
They
Marcoussis, the problem is that it is high compared to the Marcoussis
Yes,
town,
so they
which is
didn't.
quite big. It's more than 10,000 people.
Yes, and so they didn't. Finally, they didn't. So they tried to develop a project about that, but they didn't. Okay, but it's just a way to improve the power, the power usage effectiveness. Okay. So in terms of materials, so here you have the Mendeleev table, okay? And so not very. So now in all the colored boxes, so correspond to what correspond to the materials used in a smartphone, in a current smartphone. Okay. With shadow, so for example, with shadow, you have not this line, for example. Okay. It's what it was used for a phone in 1990. Okay. And with the small triangle, okay, it was used for a phone, for a very old phone in 60. Okay. And you can see, I think you can count very easily. Here you have 1, 2, 3, 4, 5, 6, 7, 8, okay, 10. Just 10 elements. Okay. And now it's half the Mendeleev table, so typically 50 elements. Okay. So you have a big increase in terms of materials used in a phone. Okay. And obviously behind this you have mining for harvesting all these materials. Okay. And so in color here you can see what, for example, this one used for the chip. Okay. This one is used for typically for the screen. Okay, and so on. So you can see the correspondence between the materials and the way the material is used. And so to analyze this, we can do a life cycle assessment, so LCA. Okay. If you want to analyze the impact of an application, of an impact of a device, so you can do a LCA. And the idea is this one. So you want to calculate all the consumption, so the energy consumption or the GHG emissions. It depends. Okay, it depends on which value you want to extract. Okay. So on one application, typically on one application. Okay, or it can be also one device. Okay. Not only by considering the use phase, but also by considering the fact that this device has to be built, or this application needs some device which you have to build. And for that, so you need to take into account the mining, the manufacturing, the transportation between some factories, and also the transportation for distribution until the shops. Then the use, and then the end of life, it means the waste. And obviously, if you do recycling, you can sometimes skip the mining phase, and you can reduce or recalculate the manufacturing phase, because obviously manufacturing a device from raw materials is completely different from manufacturing a device which has been recycled. And depending on the application, depending on the device, the use obviously is not necessarily the biggest part. Sometimes it's the biggest part, sometimes not. It depends on the material. It depends on the device. Okay. And once again, it's not very easy to have a big the whole figure about this, because sometimes you can say, well, it's half, one half and one half. For some materials, it's 80% for the mining, manufacturing, transportation, and so 20 for the use. For some other device, but the contrary, it's 80 for the use and 20 for the mining and the manufacturing. So it depends really on the device and on the application. Okay. So there are a lot of studies about LCA. Okay, with a lot of figures, with a lot of tables which are very horrible to read, and especially for the mining and manufacturing, it's not easy to know where you have to stop. And especially, for example, just for mining, do you consider the canteen of the employees or not? If not, so you need to consider the canteen. So you need to consider the food in the canteen, and so on. It's endless, completely endless. Okay. So you need, if you want to do that, you need to specify your space, the space of your study, very clearly at the beginning of the study, and you need to do that before starting. So just some values. So if you consider a mobile phone, so here it's an example about device. Okay. So for mobile phone, so typically the LCA leads to this kind of so that's carbon dioxide equivalent. Okay, so you consider methane, you consider all the greenhouse gas. Okay, and so for a smartphone, you obtain this value. So you emit around 70 kilogram of carbon dioxide. Okay, and for a dumb phone, which is much simpler, especially because the mining is much simpler and the manufacturing is much simpler because you use less element in the Mendeleev table. So it's around 10. So it's much smaller. It's not divided by 100 or by 1000, but almost divided by 10. So it's much smaller. And here you have, for example, an LCA for a laptop. Okay, so you can see that the carbon footprint is much larger. Okay, because it's not 70 kilo, but it's 400 kilos. So it's much larger. It's just much larger because it's much bigger. Very easy. Okay, you have a relationship between the size and the. Usually, you have a relationship between the size and the carbon footprint. Okay. And so here, this LCA has been done by Apple. So it's about a laptop. Okay. And what you can see, for example, because it's very interesting because you have the decomposition. Okay, between the mining, manufacturing phase and the use phase. Okay. And here you can see that the use phase is around 20%. So it means that for a smartphone, with a use phase during 4 years, okay, you have So 80%, which correspond to mining, manufacturing, transportation, distribution, and so on. Okay? And if you keep this laptop so 4 times longer, so it means 16 years, then only after 16 years you have the use phase, which is equal to the manufacturing. Okay, so keep your phone, okay, or keep your laptop. Now this one is not 16, unfortunately. My desktop is 16. My desktop in my office is 16, and I have some trouble with it, but it works. It works. But sometimes I need to open this one to do some things. Okay. And now, if you look at an application, okay, so here typically an email. So usually it's very difficult to calculate for an application. Okay. So typically you have 2 ways to, because it's very hard to estimate precisely the carbon footprint for one email. What does it mean, one email? Because you have some common infrastructure. Okay. What percentage of the data center you will consider for one email? Okay. So usually what you can do, you calculate a global value and you divide by the number of emails. Okay. But even this global value, the data center are not done only for email, but for a lot of things. So you need once again to put a percentage. So typically you consider a percentage of traffic, the percentage of storage. Okay. But even that is not necessarily true. Okay, because I imagine you know that. Even if you have no traffic in your network, you have a consumption, for example. Okay. So you have a fixed consumption and a consumption depending of the traffic. So finally, the fixed consumption, how do you assign this fixed consumption to the set of all the email and then one email? So therefore, usually you have a quite large interval for the evaluations. Okay, but usually the trends are quite similar. So we just speak about trend finally. Okay. So for example, if you have two evaluations, and so it's for 1 megabyte email, so a big email, and it's around a few milligram. So it's very small, okay, but we have a lot of emails. But here it was without considering storage, so finally without considering the data center. And without considering LCA, in the sense without considering the construction of the infrastructure, the construction of the device, enabling the transmission of the emails. Okay, so it's just the consumption due to the traffic of your email. Okay, and so in that case, it's just some milligrams. Okay, and if you consider storage and LCA, and for example, that's a value given by ADEME, which is a French agency, but the environmental transition French agency. Then obviously the value is much bigger. So you multiply by, so you remove the milligram, they just gram now. So be careful. Once again, be careful when you see a value. You really need to see what is the context of the evaluation of the number. Okay, so in some presentation, perhaps one person will consider only this value. Okay? And 1 month later, you will see another presentation and you will see this value. And you will say, oh, what's happened? No, it's rational. It's just not the same way to calculate. And one point I would like to focus also is about manufacturing. So for example, usually and especially when we do wireless network, or we focus on use phase. We try to reduce the transmission power. We try to improve the performance with the same SNR, so with the same transmission power. So finally, it's use phase. Okay? And even, for example, for some engineers or researchers in electronics, they try to improve the consumption of a chip for the use phase. So it means on the same surface, I will put more chips, but with the same consumption per surface. So finally, one chip is more efficient. Per chip is more efficient, so I can do more computation, and we can put more complex algorithm we developed and so on, okay, with the same energy consumption. But be careful. If you use a very nice technology, so it means, okay, if you consider the technology node with a very small, with a very fine line, okay, in terms of manufacturing, it's much more expensive. It's much more expensive in currency, but also in energy. Okay, so it means, yeah, okay, I improve the use phase, but I degrade the manufacturing phase. And sometimes the trade-off is not good, but usually nobody does the trade-off, calculate the trade-off. Okay. And here that's the case, okay? When you decrease, so when you improve the technology, okay, the cost in energy and finally the cost in GHG emission per surface increase. Here typically it's multiplied by 4 between this technology and this one. So finally, almost finally, after that I will go on wireless network. So here I focus on energy, I focus on greenhouse gas, but so finally I focus on carbon footprint. Okay. But obviously it's not the only footprint. Okay, there is a lot of other environmental footprints. Okay, so here I list some of them. Okay, so here they are in English and here they are in French. Okay, and so it's very difficult to. So here it was for a smartphone, and so you have the pre-manufacturing means mining, then you have manufacturing, distribution, use, and disposal mean end of life. Okay, and obviously depending on the footprint you are considering, the manufacturing is more important or not. It depends. Okay, and finally, so far I just look at this one. Okay? Global warming. It means greenhouse gas. Okay. But you have a lot of other impacts. So, for example, acidification of the ocean, eutrophication of the ocean, ozone layer depletion, and so on. Okay. And if you want only one measure, because obviously it's difficult if you have 10 measurements or 20 measurements to do a ranking. Okay. And typically, we would like to have only one measurement. And this measurement is obtained by the PEF, which is the product environmental footprint. So, well, you add some intermediate measurements. Okay. And so typically here you add, so here it's related to climate change, here it's related to ozone layer depletion, here acidification, and so on. And you have some points, some ponderations, okay, some weights. Okay. And finally, you obtain only one value. But okay. Okay, it's just a way to do a ranking. Okay, yes. So perhaps if you buy a phone, a smartphone, you will have a value for the PEF. Okay. Okay, so I already speak about that because I think I need to speed up. Okay, so now I will do some application to wireless network. Okay, and so as you know, we have a new generation every 10 years usually. Okay, so I just remind that 2G is for voice, 3G was for data. Okay, and typically for mobile internet. Okay, I say what an idea because I started to do research between at the beginning of 3G. Okay, and when I explain to my friends what I was doing during my PhD thesis, they mentioned that this PhD thesis was completely useless because mobile internet was completely useless. And especially I focus on Doppler effect. So typically when you are working and when you are in a car and using mobile internet. Okay. So 4G is just a way to improve 3G, so it's just a high data rate, okay? And for 5G, so I think you know we have three categories, okay? So one, which is just an improvement of 4G, okay? So now it's not high, but very high, okay? Data rate. So the second one is for low latency and high reliability, and the last one is for massive connectivity, and 6G is under progress. And so we can ask why it is useful for doing that, okay? And finally, is this network a solution for the environmental crisis or not? Okay. So the first solution advocated is this one. We will do green IT. So we will do green IT. So what does it mean? Green IT is just a way to do, we will do energy efficiency. So it means, okay, the performance metric we would like to see is improve compared to the energy consumed for obtaining it. So it's just a relative goal. Okay? It's not a strict goal. It's just relative goal. Okay? So it's just less typically greenhouse gas per unit. Okay? But you say nothing about the number of units. Okay? And typically you can have the so-called rebound effect where the number of units increases. Okay? And it's a very standard way. And this phenomenon has been seen often in the technology history, okay? When you improve a technology, so typically when you improve the energy efficiency of a technology, this technology is more used, and finally, the consumption of this technology is higher than before. So it means that this technical answer is not enough for fixing the problem. Okay, you need to add something. Okay, you need to add something. So the second solution, which actually is the same, is IT for green. Okay, we will do IT for another domain, for another topic, and this topic will be more efficient thanks to IT. So once again, it's an energy efficiency. So it's not an energy efficiency for the IT domain, it's just an energy efficiency for another domain obtained thanks to IT. So the goal is exactly the same. It's still a relative goal, and the goal is just deported. Okay? So once again, it's just less greenhouse gas, but elsewhere, not in the IT domain, but in another one. And this effect is called an enablement effect. Okay? So it's just a deportation of an energy efficiency. But just a way to improve another domain in terms of efficiency. And once again, you may have a rebound effect, not necessarily in the IT, but in the other domain. And so once again, this technical answer is not enough to fix the problem. Okay? So the last solution is sufficiency, so solution 3, where you, well, but nobody does that, okay? You try to say, okay, I will not improve the efficiency. Okay, I will try to build a system with a prefixed energy consumption. Energy or power, it depends if you want to divide by the time or not. And in that case, obviously, if you do that, by construction, you avoid the rebound effect because your energy is capped. And obviously, you answer an enablement effect because you avoid the rebound effect in another domain if you want to use it in another domain. But obviously, in that case, you need to limit, because if you have a predefined value for the power, sometimes perhaps you need to switch off some things. Okay, and so it means you need to have a reflection about the uses or the needs of your network or of your technical infrastructure. It's not only for IT actually. Okay, and obviously the question is by whom. And so efficiency, so solution 1 and 2 is just efficiency and it's just related to optimization. And it's exactly what we know, what we are able to do, okay? Because every day we do optimization as an engineer or as a researcher. And the last one is more related about the way of life because we need to decide the uses and the needs. So just the how many remains
10 minutes.
10 minutes.
We are
Okay.
at the top of the hour.
Okay. So the rebound effect is also called the Jevons paradox. Okay. So as I mentioned, okay, when you improve the technology efficiency, usually the use phase increases, and finally, usually the global energy consumption increases as well. Okay. But it's not necessarily direct. Okay. And here there is a list of rebound effect. Okay. So for example, obviously, if you have a very powerful 5G, okay, 5G will be developed, okay, and so you have more production of 5G equipments. You have more production for wireless network equipments and so on, not only user equipment, but also network equipment. Okay, so that's the first order. The second order, okay, 5G is more efficient, so finally you will use it more. Okay, so you will do more data transfer, you will do more video conferencing, you will do, so finally mobile data consumption will increase, and so on. So finally your infrastructures will use more energy because your infrastructure is more stressed. Okay? So that's the second order. And the fourth order, you need also to calculate the indirect rebound. So for example, if you imagine that thanks to 5G, you save time. So typically, you do teleworking, so finally you don't use your car, and so you gain perhaps 1 hour or 2 hours per day. What do you do during these 2 hours? Okay. If during these 2 hours you use your car just to work, not to work, but to do shopping or to go in the forest and so on, there is no gain. Finally, there is no gain. And you need to take that into account. So therefore, it's very difficult actually to analyze. If you want to analyze very precisely, the rebound effect is very difficult because this kind of effect is very difficult to analyze. Okay. But in the past, this effect has been seen by a lot of technologies. Okay. So typically, take the train, for example. One indirect rebound effect of the train, for example, is the development of the English coast from London. Okay, so Brighton or Southampton has been developed thanks to the train. And so finally, you need to take into account the energy of the development of this area as a result of the development of the train, and finally of the improvement of the train. Because now you just need 1 hour to go from Brighton to London. So therefore, it's very difficult to analyze. So here I just mentioned some examples from ICT. So the first one is just machine learning algorithm. So here it's very easy, okay? Because machine learning algorithm, so now works. Before they didn't work, but now they work and they are quite speed. Okay, they are quite fast. Obviously, the number of apps using them increase. Okay, and finally, the consumption of machine learning algorithm increase. Why? Each algorithm is much more efficient than 2 years or 3 years ago. If you consider the improvement of electronic devices and batteries, so finally, obviously, thanks to this improvement, you use your mobile phones. So the use of your mobile phone depends on this improvement. Okay, and what you can see is that, for example, your phone autonomy keeps the same. So it means finally you use more energy. Okay? Because if you use your smartphone 1 hour, the energy during this 1 hour is much larger than with a dumb phone. And the improvement of mobile networks obviously increase your data action. So here we have some data from France. Okay. So here that's the wireless mobile network consumption. Okay. And here we have the introduction of 4G. So it was in, not easy to see, but it was in 2013, 2014. No. And so you can see that the shape, so once again, it's still linear, but the slope is not the same as before. So you can see that, okay, you have an increase of the consumption of data, but even the shape of this consumption is modified and is increased. Just because 4G is much more efficient than 3G. Okay, enablement effect, but I already mentioned, so perhaps I will speed up.
Yeah, I think we have.
Yes, because it remains some slides. Okay, and I would like to provide some technical results. Okay, here just some figures. So here it's if you look at the introduction of between 4G and 5G. Okay, so here it's some data coming from Huawei, okay, and it corresponds to a base station, so an average base station. Okay. And what you can see is so finally, you can see that, okay, 4G is not much more than 5G is not in green, is not much more than 4G in blue, okay? But you have an accumulation. So it means perhaps it makes sense for 5G, but in that case, you need to switch off. And now, not in 10 years or in 20 years, you need to switch off 4G. And it's really not the case. Okay. So if you, perhaps for 5G, if you want to see a gain in energy, because 5G is much more efficient than 4G, okay, if you want to see this effect, okay, you need to switch off 5G. Yes.
But then you have to throw in the rubbish. Then you have to throw in the rubbish smartphones for 4G, so at the end it will not be worth it. You know, if I can still use my smartphone, it's better.
It depends, because you can do that in 3, 4. If you do that in 3 or 4 years,
Or
which
10 years.
typically correspond to the rate of replacement or to the rate of refreshing your phone, it's okay. Yes, obviously, if you do it just 1 month later, and everybody has to buy a new phone, is useless for the user equipment. Okay, but if you keep it just between 3 years or 4 years, you may have a gain. But it's really not the case. Okay? We can see that even in France, providers continue to install just 5G base station without just 4G base station without 5G base station. And usually what we have seen, but okay, the figure has been obtained last week. Okay, but what you can see is typically we start to switch off 2G. So it means when finally we install 5G now. Okay, so imagine we are installing the nth G. We switch off the n-3 generation. Okay. So it means n-2 and n-1 are still switch on. And if you have to have some gain, you need to reduce this phase. So perhaps I will. Yes, okay. Okay, I will. So now, if we want to analyze, okay, a system or a technology, so which kind of energy we need to consider? Actually, we need to consider 4 energies. So the first one is the transmission energy, and usually is the only one we consider in our paper. Okay. The second one is processing energy, so the energy used for decoding, for synchronization, and so on. So usually this one is omitted. Okay. Or you just say, okay, I have developed a nice decoding algorithm with a less complex, which is less complex. That's all. Okay. But you don't know exactly what is the pre-processing, and we don't know. Okay, perhaps it's less efficient. It's less complex, so it's a little bit less efficient. So in fact, you need to increase PTX, your transmission energy, but finally you don't know the trade-off. Okay, so the gain in pre-processing perhaps is completely absorbed by the loss in transmission energy. Perhaps yes, perhaps not. So the third one is the power of circuitry. So you need to consider power amplifier, ADC, and so on. And the last one, and you see the last one is much more complicated, okay, because it's not used during the use phase, is the manufacturing energy. So that's related to LCA. So perhaps I will skip this one. So obviously we know, everybody knows channel theory here, okay, or channel capacity. So we just know that if you want to increase the energy efficiency of a system, it's very easy. If you consider just the transmission power, you just have to increase the number of independent channels. And for doing that, you just have to increase the number of antennas or to increase the bandwidth. If you do that by construction, you decrease the transmission energy per bit. So you increase the energy efficiency, okay? But you just improve the energy efficiency related to 1 energy out of 4, okay? And that's an issue, okay? That's an issue. So perhaps now I will focus on 2 examples, okay? So the first one is a macroscopic analysis done by some researchers from Louvain-la-Neuve in Belgium. Okay? So they try to calculate the impact of the introduction of 5G. Okay, so they consider a consumption model for 4G, and usually you consider an affine model where the power used, and usually without considering manufacturing. So here you consider the transmission, you consider the circuitry, and you consider the processing. And here they consider the manufacturing, but a fixed value. It means, okay, we haven't, this network is used during 10 years, the manufacturing phase, the cost of the manufacturing case is this one, I divide by 10, and that's okay. Okay. And then you have an affine cost, so a fixed P0 plus a cost depending on the rate, so finally depending on the traffic. And for the 5G, so they consider a model. Okay. They consider that we can take the value for the 4G, multiply by an improvement factor beta, because IDC will be more efficient, power amplifier will be more efficient, and so on. Okay. So beta typically is less than 1. But you need to correct but the fact that the bandwidth is larger. Okay, so perhaps your power amplifier with the same bandwidth is more efficient, but the bandwidth of the amplifier now is larger. And so it's more difficult to build. Okay. And so you have 2 correction terms, one about the bandwidth and one about the number of flows. So typically the number of users, if you want. Okay. And thanks to some data, but usually some data obviously not related to 5G, because they didn't. They just have some data from 3G and 4G. Okay, so we try to do a regression to obtain the value for beta, the value for the power. And so finally, we obtain this kind of model. Okay, and we obtain this figure. Okay, so in orange it corresponds to 4G. So here it corresponds to the static part, so P0, and here it corresponds to the dynamic part, so the alpha times R. Okay. And you have a traffic improvement. So I don't remember which one. Perhaps it's a growth rate of 10% per year, something like that. And so here in 2020 and here in 2025. Okay. And here they consider that a part of the traffic now is done by 5G. Okay. So they reduce the traffic for 4G, and this traffic is reported to 5G. Okay. And typically here we see the transfer rate is increased. Okay. And here they consider that all the traffic is done by 5G. And here you can see a small gain with more traffic, compared to the 4G. So it depends on the model, typically on the value of alpha, of beta. And so. Okay. So once again, they mention, okay, if you want to have a gain, you need to switch off 4G. Okay. And here perhaps the last example before stopping. So here we did a microscopic analysis. Okay. So here we consider a model for 4G, so just 4 antennas, and we consider that we have already 4G. So it means that the manufacturing phase has already been used during 10 years. Okay. And now we introduce 5G. Now we introduce 5G, and we introduce with massive MIMO, so typically 100 antennas. Okay. And here we take into account the manufacturing cost, okay, and divided by the number of application of your technology. So it means, so here we consider the depreciation year. So here when I consider 10 years, it means that I have 5G for 10 years, and I have 4G for 20 years. Okay. And so we consider manufacturing, and we consider also that doing manufacturing for 5G is more expensive than for 4G because you have more antenna. And in that case, what you can see, so here it's in black, you have no traffic increase, okay, but the same traffic. And so the black, so this is the black for 4G, and this is the black for 5G. So you can see there is no gain. Because you have a cost just for building the 5G. Okay. And if you increase the traffic, so here it's 10% per year, it's 20% per year, and it's 30% per year. Okay. Now it's around 20%. Huh? Okay, so more the red curve. Okay. So for example, if you consider the green one, okay, so it's between 20 and 30 now. Consider the red one. Okay. If you consider the red one, okay, you can see that after 7 years, it's useful to have developed 5G. So it means that the manufacturing cost has been absorbed by the gain in traffic, okay, or by the gain of the use phase. And I think that now I can conclude. So here just, okay, another one. Yeah, just to conclude. And so now it's you want to design 6G, okay, because we are designing 6G. Some researchers are designing 5G. Okay. If you look at the paper about 6G, there is no, but the same. Okay. For me, there is no learning about the 5G controversy and the way to build the 5G. Okay. It just for me the show must go on. And typically, if you, well, I just mentioned 2 papers, but I can mention a lot of papers. Okay. So there is some idea to improve 6G. So one example, for example, is to use solar panels. Okay. So not on the base station, but on not Zeppelin. But if you look at the paper, for example, the energy cost in that paper of the solar panel, of the Zeppelin development, of the fact that the Zeppelin has to turn around the Earth is 0. It's 0. So finally, they replace the cost of the base station by 0. So for me, it makes no sense. It makes really no sense. And that's the same thing, for example, in some paper about reflecting intelligent surfaces. Okay, it corresponds to an electromagnetic mirror. Okay, and usually, once again, the energy cost of the use of this, typically of the manufacturing of these reflecting intelligent surfaces, are 0. And I think we cannot do that anymore. We did in the past. Okay, we did in the past. Typically, when we analyze relay channel, typically the relay was for free. Okay, but I think okay, in 20 or in 2010, we can do that. Okay, because we are not necessarily aware of this kind of consumption. Okay, but now we are aware. So I think we need to do differently. Okay, I think I will stop here. Really enough. Okay.
Thank you.
Thank you. A little bit too long.
So I think people have to go. But
Yes, because it's free.
Maybe we take the question.
Yes, I can. Yes.
I have a small question.
Mhm.
Yeah. So actually, I'm working in the field of the network monitoring and the network measurement.
Yes.
Yes. So actually, recently we have been focusing more on the monitoring budget control. It's a new word for me. Like, in other words, when we monitor or optimize the performance of the system, we are no longer just looking for the performance, the more measurement or the larger granularity. So, but also we considering the computational, the storage, and even the energy consumption of the measurement themselves.
Yes.
So yeah, so you have just mentioned a new word, like it's a new word for me. It's the rebound effect, right?
Mhm.
Yeah. So I have a small question, like in the for now in the real-time network analysis and the smart traffic classification and the large scale the telemetry, could the measurement more actually add extra load can be seen as a kind of the rebound effect.
But
Like-
you can see it if you can already see it, for example, okay? If you consider this figure, this one, for example. I think it was this one. No, I don't remember. No, it was one. Yeah, this one. So here is not energy consumption, so it's just data right or traffic, okay? So you can already see it on the traffic. So finally, obviously, you can, I imagine, also see it in energy consumption. So it depends on what you want to do. If you want just to see, okay, there is an increase of the traffic, so there is an increase of energy consumption. Obviously, you can see it by your telemetry, okay?
Sometimes the purpose of a paper, for example, is for saving the energy. Like we involve some AI technology, like AI models, to help the system saving.
Yeah, but in that case, you don't consider rebound effect. In that case, it's just optimization, okay? It's just this, okay? So you try to introduce AI or whatever you want, okay?
Yeah.
You want to find a new algorithm, okay? Just to, I don't know, to do a better scheduling, to do a better even energy harvesting, to do a...
Yeah.
So it just you improve your performance metrics given an energy consumption. So it's just optimization. And you don't know if this optimization, so you can imagine that if the traffic is the same, okay, if the traffic is the same, if the network is the same, so typically if the number of bits is the same, the use phase will decrease. The use phase consumption will decrease. But it's not the whole story. Because usually when you do an optimization, okay, the traffic will increase.
Yeah.
And so you increase per bit, but the number of bits increases.
It's a hardware resources.
And so finally, okay, you have a better algorithm, but this algorithm enables you to finally consume more. It's exactly what's happened for AI, okay? Before ChatGPT, there is no consumption or a very small consumption for translation, okay? Because you do your translation by yourself.
Yeah.
Okay? And now, okay, you write a small text, you send on the cloud, and you obtain the solution. So you increase by construction in that case, just before the algorithm is better, and you consider that the solution is better than before. So that's your performance metric, okay? The score for translation is better. And the application is more used. So if you want to do it, if you want to, obviously it's a little joke, but if you want to increase or to decrease the energy consumption, works badly. If your optimization is very bad, your system does not work and is not used.
Yeah.
And finally, the consumption is zero. Ah, it's a little joke. Okay.
Yeah.
But it's not so a joke. Okay? It's not so a joke. So just optimization is not enough. Okay? But we do that. I know. I did that during 20 years. So we do that. Everybody did that. But usually it's just a relative goal. And I think we need to work on absolute goal, absolute value. Usually we can do that. It's just, okay, I can say, okay, instead of minimizing the power, I will try to maximize something such that the power is limited by a value. Yes, but usually you do that for one cell. Okay, you do that for one cell, and typically if you increase the number of antenna, for example, if you increase the number of antenna for solving this problem, you need to take on the fact that you need to build your antennas. You need to manufacture your antennas. And usually it's not considered. But it's very difficult to consider because you need to understand what does it mean, a new antenna.
Yeah.
Because obviously you have an evolution also of the technology on the antenna. So for example, so here in my derivation, it was too simple. For example, I consider that the cost for building a base station, okay, is not only proportional, but there is a part proportional to the number of antennas. But the way to build 4G antennas with just a linear array of 4 antennas is not the same as building a massive MIMO with 100 antennas, which on a square, the frequency, the bandwidth, and so finally, is not necessarily proportional to the number of antennas. But to know the model, if you want to do an optimization, you need a model. And having this model is very difficult. So we are working on that currently to have an idea on how it works with a lot of parameters, not only number of antennas, the bandwidth, the power, the number of power amplifiers. So it depends also if you do an hybrid beamforming and not an hybrid beamforming. It depends on a lot of things. Okay? And we want to try to have a clear idea because the ideas are not clear. In our minds, okay? And even so, there are some papers about that, but usually they just focus on one point, or they consider that the bandwidth is fixed, and they look at just another parameter, and another paper will consider this parameter fixed, and we just look at the bandwidth and so on. So it's quite horrible to understand especially to have a good view of the trends. So we try we are working on that, to have a proper idea of a model, and especially to imagine typically what can be the consumption of a 6G base station without having a 6G base station. But by considering manufacturing, okay, by considering circuitry, processing, circuitry, and manufacturing. Yes.
Do you need
Thank you. So, like a word of hope at the end of this afternoon, what should we be working on?
I will not answer.
Okay.
No, I think we can, but obviously you will do that slower. For example, if you want to take it into account all the energy, okay, if you want to do something which is quite nice and clear in terms of consumption, so it means you need not only take into account transmission energy, but also the other ones. And in that case, obviously, you need to spend time on that. And it's much slower.
Yeah, I guess so.
But for example, if you do reflecting intelligent surfaces, I think it could be nice if you consider the cost of manufacturing this. It's not for free. Even if you consider it's passive, it's not for free for manufacturing, and even it's not completely passive because you need to modify the phasing. So there is a little cost, okay? Okay, there is no decoding, re-encoding, and so on, okay? But there is a cost, okay? These surfaces are plugged somewhere, okay? And even if you have a solar panel, okay, but in that case, you need to consider the solar panel, okay? Once again, it's not for cost. Even if it is carbon-free, almost carbon-free, it's not for cost. It's not for free. Okay? So I think you can continue to work on that. And even I think there is some nice challenges. Okay? But just by being more precise. And it means slower. Okay? Because it's spending time to do that. And I don't know if it will be appreciated in IEEE transactions. I really don't know.
Yeah.
I never tried to publish this kind of work in IEEE transactions. So I don't know if they would like to consider, and they would like that, okay, perhaps technically the paper is not the best algorithm we can develop, but this paper has a big view on the real view, on the fair view, on the energy consumption of what the paper developed. I don't know if it will be appreciated. I don't know. I really don't know. I think it will depend on the reviewers, but
Maybe
but I think we can still work because we need some networks. Okay, it will be very difficult to have no wireless network now. Okay, but I think that the way we are building 6G is the same way as 5G, and I'm not sure that's a good way.
Point taken. Thank you very much. Thank you, everybody.
Okay.